Hi everyone, this is lesson 7, Finding Limits by Analytic Methods. So you should be on pages 32 to 34 of your packet. We've got 3 learning targets for today. I can calculate the value of a limit algebraically using substitution. So we've done the value of a limit from a graph. We've done it if we just kind of know what the graph looks like in our heads by just looking at the function. We've done it from a table, and we've done it using algebraic limit properties. So now we're going to do it using substitution. We also are going to work on identifying limits that are in indeterminate form. So we're going to talk about what that means. And the last thing is I can use factoring to simplify a function in order to determine a limit. So we're going to be reviewing how to factor really quickly. So the big idea for today's lesson is this substitution theorem. And hopefully you already know what the word substitution means, but we're going to really dive into it. So the substitution theorem says that if we want the limit of f of x as x approaches c, it's really just equal to f of c, which is the function value at c, provided that f of c is a real number. So let's talk about what that really means. This really means that we can evaluate a limit by substituting the x value that we are approaching into the equation we are given, provided that we get a real number for our answer. So this sounds a lot more complicated than it really is. All we're talking about is if we want to find this limit, so we can evaluate this limit, so the limit of f of x as x approaches c, we can evaluate that by plugging the value of c into our function. So let's see what this really looks like. We have this example here where substitution works. It says evaluate the limit of x squared minus 4x plus 3 as x approaches 5. So you'll see here it says x approaching 5. All we're going to do then is take that x value 5 and plug it in anywhere that we see an x in our function. So that means we're going to have 5 squared minus 4 times 5 plus 3. So we get 25 minus 20 is 5, plus 3 is 8. So we got a value. The function value at x equals 5 is 8, and that also means then that that happens to be our limit this time because there's nothing weird going on. Really, that's what this means. Substitution works as long as there's nothing weird going on with your function at that x value. So let's take a look at an example where substitution actually fails. So we're doing the limit of x squared minus 25 over x minus 5 as x approaches 5. So we're going to take this x value of 5 and plug it in for x. When we do that, we get 5 squared minus 25 all over 5 minus 5. Now we know that 5 squared is 25. 25 minus 25 is 0. And we get 5 minus 5 in the denominator, which is also 0. So we end up getting 0 over 0. And really, we know that this is not a real number. Right? We know that we are not allowed to divide by 0. Plus, 0 over 0 is kind of a weird thing, right? So we're going to talk more about what that means in a little bit, and we're going to talk about how to deal with limits that give us something like that. So in this section, we're going to discover one of the methods, and then later on in this unit, we're going to talk about a couple of other methods that we have, or procedures that we have for dealing with limits that come out like that. But for now, let's look at some examples where we are going to use direct substitution. To save some time in this video, we are not going to do all of the examples here. I want to do 3 of them because there are 3 of them that I feel like we're going to need a little bit more explanation on because they're the ones that students tend to struggle a little bit more with. So we're going to focus on number 3 first. We have the limit of 4 times the natural log of x as x approaches e. So the first thing we're going to do is we're simply going to substitute in. So it's 4 times the natural log of e. Well, we need to figure out what the natural log of e is. This is a function that you should be comfortable working with, at least with some of the basic values, okay? So what we're going to do is over on the side here, I'm just going to take the natural log of e and I'm going to set it equal to x. I want to figure out what it is. So we have to remember that natural log really just means log base e. And so what we're going to do is we're going to rewrite this as e to the power of x equals e. We're going to do a log circle. Hopefully that sounds familiar. So we can clearly see then that this natural log of e is really equal to 1. So now we have 4 times 1, which is equal to 4. And again, that's because this e over here, sorry, it's e to the x equals e to the, there's a little exponent of 1, right? That's where we get that 1 from. Let's take a look at number 5. Number 5 says the limit of sine of 2 theta as theta approaches pi over 3. So our variable looks a little different, right? We have theta instead of x, but it's still the same idea. We can still use substitution here. So we're going to do the sine of 2 times pi over 3. And really, we know that that's the sine of 2 pi over 3. And this is going to be where knowing your unit circle is really something that's important, all right? And this is something that you are going to be expected to know. So we know on our unit circle that 2 pi over 3 is over here. Oops, that wasn't a very good representation of it. A little bit more like that. There we go. So we know that this is 2 pi over 3. If we think about what the coordinate point is that goes along with it, that's a negative 1/2 for our cosine, and the square root of 3 over 2 for our sine, for our y value there. Again, this is something you should know and be comfortable with, is the unit circle. And so if I want the sine, that's my y value, so that's just root 3 over 2. One more example for us to look at over here is number 6. So we have the limit of log base 2 of x minus 4 as x approaches 8. So we're going to go ahead and plug in 8. So it's log base 2 of 8 minus 4, which is 4. And we need to think about what that really means there. So if I go over here and just say log base 2 of 4 is equal to x, this is actually very similar to number 3. We can do kind of that log circle that we should remember. So this is going to be 2 to the x is equal to 4. So 2 to what power equals 4? We know the answer there is 2, right? 2 squared. And so the answer to this limit is going to be 2. So again, even though these are just some basic substitution ones, these are functions that we have to know how to evaluate. So I wanted to address those 3. The other 3 are pretty straightforward. I really encourage you to try them and just make sure that you are comfortable doing that. So this next part is about evaluating limits that are indeterminate in form. So this is dealing with that second learning target that we talked about at the beginning, this indeterminate form. So something important here is we are always going to try direct substitution first. Sorry about that. Always, always, always try direct substitution when you are asked to find a limit. If you get 0 over 0, or if you get infinity over infinity, And that could be plus or minus for both of those. So I'm going to put that there. But 0 over 0, or infinity over infinity, we call these limits indeterminate. Literally, we're not able to determine the form right now, so they're indeterminate, okay? We will learn one of several algebraic processes that we will use to find the value of a limit that is indeterminate. An indeterminate limit requires us to manipulate the function using algebraic techniques before trying substitution. These three most common algebraic techniques that we use are factoring, multiplying by a conjugate, and simplifying a complex fraction. The only one we are going to worry about right now is factoring. Later this semester, we will also study L'Hopital's rule, which is another method we can use to evaluate limits that are indeterminate. So as of right now, we are just going to focus on the factoring, and everything else will kind of come in later. So let's take a look at this first example here that just says evaluate the limit using substitution. So again, we know that the first thing we are going to do is try direct substitution. So we're going to take that x value of 2 and substitute it into our function. So 2 squared plus 2 minus 6 all over 2 squared minus 6 times 2 plus 8. So we get, let's see, 2 squared is 4, plus 2 is 6, minus 6 is 0. 2 squared is 4, minus 12, and then plus 8. So we get another 0 down there. So we get 0 over 0, and we know that that's a problem, right? This is indeterminate form then. You have to write anytime you get 0 over 0 or infinity over infinity, you have to write the words indeterminate form on your paper. All right, it's very important that you acknowledge that there is a problem here. So what we're going to do then is we tried direct substitution and that didn't work. So now we're going to try it by simplifying first. So I'm going to try and factor this function here. And by the way, I should acknowledge the fact that this is a rational function, right? It's a polynomial on top and a polynomial on the bottom. So this is a rational function, and a lot of times those types of functions are the ones we're going to be factoring. So the limit as x approaches 2, and we're going to go ahead and factor. So on the top, I know it's going to be x and x. Let's say I want to multiply to negative 6 and add to 1. So that's going to end up being plus 3 and minus 2. And then on the bottom, multiply to 8, add to negative 6. So that's going to be minus 4 and minus 2. The biggest thing about factoring that everybody tends to struggle with is just mixing up your signs. So make sure you are super, super careful there. On the top, we've got a positive 3 and a negative 2, and on the bottom, they're both negative. And so we have a 4 and a 2. But we can see then this x minus 2 cancels out. And so what we're left with is the limit as x approaches 2 of x plus 3 over x minus 4. Now we're going to try this substitution again. So when I do that, I get 2 plus 3 on the top and 2 minus 4 on the bottom. So I get 5 over negative 2. So negative 5 over 2 is my limit. So I wasn't able to find it in its original form. I had to manipulate it a little bit to be able to actually find my answer. So now if I look at the graph of this, we're going to look at kind of connecting these representations here. So we tried direct substitution, got indeterminate form. So we factored and canceled some stuff, and then we were able to actually find the limit. Well, if we look at the graph here, I want to find the limit as x approaches 2. So as I approach from the left and as I approach from the right, my function is approaching wherever that hole is. And actually, we're lucky, it's shown right here for us. So the limit there is going to be negative 5 over 2. And so in this case, we're actually able to see that the two limits are equal, right, when we did the algebraic manipulation and when we look at the graph, which is a good thing. They are equal to each other. So a couple of notes about factoring that are actually going to help us get a more accurate representation of the graph, even if we didn't have the graph. So the first thing we want to talk about here is if a factor cancels from the numerator and denominator of a rational function, then the graph of that function has a hole at that x value. So I'm going to grab a color here. Let's go ahead and do pink. So for this first one here, we're looking at something that canceled. Well, we can see this x minus 2 canceled when we factored. And if we look at our graph, we can see that at x equals 2, that's where that hole is. All right, so that's really what we're showing here. Because we factored this function and we canceled that x minus 2, now there's a hole at x equals 2. For this second one here, this second note says if a factor of the denominator does not cancel, then the graph of that function has, cross this off actually for me and put a vertical asymptote. At that x value. So when we look at our graph, or actually let's look at our function first, excuse me. This x minus 4 did not cancel when we factored. We can see that it's still right here, which means at x equals 4, our graph has this vertical asymptote, and we can see that clearly right there. So again, the reason we're kind of talking about this is because we have to be able to start looking at these functions and getting an idea of what the graph already looks like. And so in this case, we know if we factor in something cancels, that has created a hole at that point. If we factor and the denominator doesn't cancel, that's created a vertical asymptote. So it just kind of helps us to connect a little bit more with these representations. We're going to look at just a couple of quick examples, and again, to save some time on the video, I'm not going to do all of them. So number one you can see is just a direct substitution. There's no issues there. However, number two, I see a rational function, and I'm thinking that that might cause me to have some problems there. So I'm going to go ahead and try my substitution and see what happens. So if I plug in x equals 2, I get 3 times 2 squared minus 7 times 2 plus 2 all over 2 squared minus 4. So I get 3 times 4 is 12, minus 14, which is negative 2, plus 2, which is 0. And in the denominator, I have 2 squared, which is 4, minus 4, which is 0. So again, we have to write that this is our indeterminate form. Which means I'm going to go ahead and try to factor this then, right? As of right now, that's the only tool that we have in our toolbox. So let's go ahead and try factoring. The limit as x approaches 2. So I'm going to have 3x and x. Let's see. I think that's going to be minus 1 and minus 2. Because that'll be negative 6 and negative 1. Yep, that works. And on the bottom, I have the difference of squares. So I have x plus 2 times x minus 2. So I can cancel those. Now, based on what we just said, that means this graph must have a hole at x equals 2. Because we factored and canceled it, there's a hole there. So now we're left with the limit as x approaches 2 of 3x minus 1 all over x plus 2. Now we're going to try that substitution again. So I get 3 times 2 minus 1 all over 2 plus 2. So I get 5 over 4 as my answer. So again, we tried that direct substitution and it didn't work. So we called it indeterminate form because that's what it is. And then we tried to factor and we were able to actually find the limit. Let's take a look at number 3. We can see again that number 3 is a rational function, so it looks like there might be something weird going on here. So if we substitute, we get the square root of 3 plus 1 minus 2 all over 3 minus 3. So I get the square root of 4, which is 2, minus 2, which is 0, and in the denominator, I get 0 as well. So we need to go ahead and write that this is indeterminate form. And when we look at that problem there's nothing that we can factor. So as of right now, we just have to write indeterminate form, and we're going to move on. We're not going to do any of the algebraic manipulations that would be required to get that one. So let's go ahead and move on to number 4. Number 4 says the limit of 5x plus 1 to the 3 halves as x approaches 3. So let's go ahead and just substitute that in. So we get 5 times 3 plus 1 to the 3 halves, which is 16 to the 3 halves. And the only reason I want to do this one is because we need to talk about what to do when we have this rational exponent like this. So if we think about our properties of exponents, this is really 16 to the 1/2 power raised to the 3rd, right? 1/2 times 3 would give us that 3 halves there. Well, we know that 16 to the 1/2 power really means the square root of 16, and then we're going to raise it to the 3rd power. Well, the square root of 16 is 4, so we have 4 to the 3rd power, and we know that that is 64. So when we look at these rational exponents here, we can see that whatever the denominator is, so in this case that 2, that's why we take the square root. So there's not really a 2 that we write in there when we say square root, but the denominator of your fraction is going to become the index of your root. So in this case, it's a square root. And that 3, which was the numerator, really just gets to go outside and becomes your exponent. All right, and we'll talk more about that. We'll do some examples of that in our warm-up when I see you all. Okay, one last thing. We're going to do this real quick. This is finding limits of piecewise functions. So really the key here is we need to look at wherever the breaking point of the function is. All right, so if we take a look at this first example here, this one is a one-sided limit. We're looking for the limit as x approaches 1 from the left of g of x. Well, 1 from the left means we want to be less than 1. So if we're doing a one-sided limit, we're simply going to substitute into the function that is tied to x is less than 1, which in this case is just x plus 1. So if we go ahead and substitute, that's going to be 1 plus 1, which is equal to 2. That's fairly straightforward for us, and we don't really have to worry. Looking at number 2, though, this two-sided limit, we're looking for the limit of h of x as x approaches 2, and we can see in this case that 2 is our breaking point, which means we're going to need to look at the left and right limits of this function. So if I wanted to do the limit as x approaches 2 from the left of h of x, then that means I'm going to plug into this top function here. So it's going to be, what, 2 squared minus 4 times 2 plus 7. And so we get 4 minus 8 is negative 4, plus 7 is 3. And then let's go ahead and do the limit as x approaches 2 from the right of h of x. Means we need to look at when x is greater than 2. So that's going to be this bottom function here. So that'll be negative 2 squared plus 4 times 2 minus 1. So negative 4 plus 8 is 4. Minus 1 is also 3. And since our left and our right limits are equal to each other, we are able to say that the overall limit is 3. So whenever the limit that you're looking for is your breaking point, you do have to check both functions. Now, really quickly, there's a common mistake that happens here. So we've got this function g of x, and we can see that the breaking point is 1. So that's really where this problem is going to be with this function. But what we're looking at is we're looking for the limit as x approaches 2. And so if we look at a number line here, 2 is over here on the right. Now if I need to do a two-sided limit, I have to look from the left and the right. So I'm going to look at approaching 2 from both sides. But either way, when I'm approaching 2 from both sides, I'm still going to be greater than 1. So for this piecewise, I only care about this function. It's actually pretty straightforward. I'm just going to do 2 cubed plus 1. So I get 8 plus 1, which is 9. So the common mistake here is that everybody seems to think that we need to plug it into both functions to check both sides, but we know that if we're approaching 2 from the left and the right, we're still going to be greater than 1. So we only care about the function where x is defined as greater than 1. So I know this last part here I kind of rushed through. I didn't want your video to be too long. So we will do some practice together in class when I see you next. If you had any questions, please make sure you wrote them down. Thanks for bearing with me through this long video.